Okay, what does the kth DFT coefficient correspond to? Okay, so let's assume that xn is a discrete time signal, and we compute the endpoint DFT of xn, and let's call it xk, summation n from 0 to n minus 1 xn e to the minus j 2 pi k n divided by capital N. K goes from 0, 1 all the way up to n minus 1. So I assume that xn is a discrete time signal and it is non-zero when n is less than 0, and it is non-zero when n is greater than or equal to n. So xk is the corresponding endpoint DFT, and we use fast Fourier transform algorithm to compute xk. Now the question is, let's say I have this xk0, okay, specific xk. What does this or which frequency does this correspond to? Okay, which frequency? Which frequency? Okay, so I'm going to answer this question now. So we will start with the continuous time Fourier transform, CTFT, x of e to the j omega, oh sorry, x of j, let's just start like x of omega, integral from minus infinity to plus infinity, x, let me put a subscript here, xat to indicate that this is an analog signal, xat e to the minus j omega t dt. Okay, omega is equal to 2 pi f. Okay, f is the actual frequency, omega is the actual angular frequency. So this is my definition of CTFT, or this is the definition used in Oppenheim's textbook, DSB textbook, as the continuous time Fourier transform. So what does this xk0 correspond to? Okay, let's try to answer this question. Now, let's try to evaluate this integral using Riemann sum. And we have to sample this xat to evaluate a Riemann sum. Okay, so xa of omega is approximately equal to summation over n, going from minus infinity to plus infinity, xa of nts. This is my sampling frequency, sampling period rather, xa of nts, okay, e to the minus j omega nts, okay, instead of dt, now I have ts. Okay, so this is the Riemann sum approximating the integral. Now I replace t by nts and dt by ts. And I get the Riemann sum. Now we define the so-called normalized angular frequency little omega, normalized angular frequency little omega, as omega times ts, or capital omega times ts. Capital omega is the actual frequency Ts is the sampling period. Okay, sampling period. So we sample this XAT with the sampling period Ts. So this XA of omega becomes summation n from minus infinity to plus infinity. I need a longer pen. N from minus infinity to plus infinity. Xn, this is now a discrete time signal, e to the minus j omega n, e to the minus j omega n, because little omega is capital omega times ts, and I have this n, and I have also this additional ts factor, but that's just a constant. It's ts here. And xn is the discrete time signal, which is the sampled version of xa and ts. So n goes from 0 plus or minus 1 all the way from minus infinity to plus infinity. Okay, so I have now this expression t sub s xn e to the minus j omega n. This is basically the so-called DTFT, discrete time Fourier transform, x of e to the j omega, summation n from minus infinity to plus infinity, xn e to the minus j omega n. Okay, DTFT is defined in this manner. And the relation between this little omega and capital omega is given by this expression. Okay, so we have to now establish the relation between x of e to the j omega and the DFT, discrete Fourier transform, which is evaluated using the fast Fourier transform. DFT, I wrote it up there, but let me write it once again. xk is summation n from 0 to n minus 1, xn e to the minus j 2 pi kn divided by capital N. DFT is similar to DTFT. However, this is a discrete transform because k goes from 0, 1 all the way up to n minus 1. And it's a finite sum. The other one is an infinite sum. Now, if most of the energy of xn is in between n is equal to 0 and capital N minus 1, or if xn is a finite extent signal, then the DFT xk is approximately equal to x of e to the j omega evaluated at omega 2 pi k over n, and k goes from 0, 1 all the way up to n minus 1. Okay, so this is how we can establish the relation between DFT and DTFT. Once we establish the relation between DFT and DTFT, then we can establish the relation between DTFT and CTFT and find out what xk0 correspond to. Okay, and we should use this normalized angular frequency relation. Little omega is equal to capital omega times Ts. So let me move this paper up.